Okay, everyone, we're going to enter the last session, the third session. You can come back to your seats and we can start the session, okay? Hopefully we can finish by 17:30. And of course, Indonesian style, we have photo session at the end, okay? Okay, so we'll continue with the next talk. I would like to invite again Prof. Audrey to the stage. And lastly, we're going to talk about green chemistry, right? So green chemistry, but green and sustainable. Please, warm applause for Miss Audrey.
So now it's working.
Okay,
How you doing?
we're good.
Woo! It's only the beginning, guys. Okay, so we need chemistry, but green and sustainable chemistry. Yay! So name everything that you can see in this room that is not a chemical. No? You don't like my question? Sorry?
None. All us is chemicals.
Thank you very much. What's your name?
Yeah.
Liga, you win.
Okay, thank you for so wonderful.
Yeah, so Riga has it. Everything is chemical. So chemistry is all of us, right? It's everywhere. It's we are chemistry, right? So chemistry is really an interesting field to be. I mean, I'm really proud to be a chemist because it's so interesting to look at the world through the lens of chemistry because you find that it's everywhere because it helps us do things. It helps us achieve things. It has function, right? So when you look at chemistry, one of the question that you can ask is, what is the function of these chemicals? Typically, they're doing stuff for us. We have colors and pigments. So we're surrounded by beautiful people dressed in beautiful clothes that have dyes and colors. And of course, these are the reason why we have these chemicals. We have a number of useful materials that serves purposes for us. Again, materials that are flexible, things that are harder here so that it collapse, or these plastics that are shaped into looking like plants, and drugs that are, of course, going to save us if we have medical needs. High-tech components are, again, our phones or food additives, etc., etc. So the function of that the chemicals are occupying is really central, and this is why we make them and why we use them. But they also come with risks, right? The fabrication of all of these chemicals comes with consequences such as contaminated water. We use natural resources that are depleting, or also the mining of these resources is going to cause pollution. We use chemicals to maximize profits, which can also come with risks because we don't really take into account some of the challenges in terms of the environmental impact. We discussed that. Risk can come as well in the accumulation of their wastes. That's a good example. The good example of that is plastics. We have chemical plants accidents, and processes and materials can also cause climate change. We discussed that as well in the session earlier. So if we look at the function, we can really see the development of chemistry being associated with a lot of good impact for us. For instance, the life expectancy of humans has been going up steadily since chemistry started to be applied to our lives. And especially at the turn of the 20th century, you can really see that the population has kept growing. It's due to the development of drugs, but it's also due in a large part to the development of fertilizers that are allowing us to sustain the growth of the population. You can see this here. The production of cereal has been going up in a linear fashion for the last 60 years, right? And what's really interesting is that it's gone up as a function of the growth of population. And what you can see too is that the production is actually heavily correlated to the yield. So what we do here is that we're not necessarily applying more land to cereal production. And you can see here that the land use has actually been pretty steady over that same period of time. But the production has been gone up because we've been able to make cereals yield better. And that's through the use of chemistry and fertilizers in particular that's allowing to do that. On the other hand, our the way that we fight diseases has been also being more and more efficient. And you can see here that this is an estimated number of deaths due to diarrhea diseases, which is really a leading cause of death in a developing world still today. But it's really been steadily going down over this period of 40 years. And that's because, again, chemistry has been here to help us through the development of drugs, or also different preventative measures, such as the chlorination of water, disinfection, that is also helping with reduce contamination so that there's less of these types of diseases. So overall, chemistry is everywhere, and chemistry is everything. Chemistry is helping us in developing our current way of life. You could see chemistry being applied to a bunch of different things, again, from functional materials like electronic devices, via food, via the development of different objects that we have around us. And we consider that more than 96% of all the manufactured goods are actually done through the use of chemistry. And this is through the development of synthetic fabrics, electronics, food packaging, medicine, aerospace equipment, automotive parts, etc., etc. We consider that there's 70,000 chemical products sold around the world today. So this is an example of how it occupies our life as well, everywhere we live, coming from the manufacturing industry to the drugstore to the gasoline station, to where we live, our house, and all the things that we have in our house, including the soaps, the baking soda, the cosmetics, the perfume, the toothpaste. We have the warehouses where we stock the materials. We have farming as well, which is using a lot of chemistry, including fertilizers, pesticide, fungicide, etc. The transportation system is really big as well. And so this is really to tell you how chemistry is really everywhere and really occupying all the corners of our lives. What was the design statement for today's chemistry sector? So what has been really the mechanism by which people have developed chemistry has been to always put performance first. So what we want is design materials that are going to have a certain performance. Again, it's linked to function. You want a chemical to do something. It has to smell good if it isn't a perfume, or it has to be really resistant to strain if it is a plastic, for instance, or it has to be or it has to have a biological function if you want to put it in a drug and help you cure cancer, for instance. So again, the function is really paramount, and the performance is really what's going to define whether your chemical does well or not. So again, if you look at all of these different areas of human activity, from oil and gas, energy, retail, apparel, finance, tourism, automobile, in all of these places, chemistry is used, and in all of these places, chemicals have been designed to perform at their best possible, in the best possible way. And also another design principle of the way we're making chemistry is we do it in a linear way. Why are we doing it in a linear way? Because what we care about is the function. We care about the chemistry to be here, to be a bottle and hold the water. What happens before, what happens after, we don't care. This is why everything has been built to be linear. We take something from the ground, we turn into an object, we use the object, all that matters. The rest, we don't care. And that's the problem with this design principle, obviously. So you've seen this repeatedly. I don't want to spend too much time on it. Resource generation, production, use, which is often, or for single-use stuff, very limited in time. You think about a car, the use can be a long time, though. Really depend on what you make, and then eventually end of life. And hopefully recycling, and which would help us go beyond the linear thinking that we. So this way of thinking about the chemical sector, which is intrinsically linear, has been translated in the way we think about chemical processes. Again, that we have thought about chemical processes up to really recently, which also is linear. So this is why a lot of the chemistry we do is done in batch, right? Because in batch, we think about things in a linear way to take raw materials and then generate products and waste. And that's our thinking about and doing things in a very linear. This is, of course, leading to great challenge and limitations in terms of our ability to sustain, again, going back to sustainability, to sustain that across a long period. This is really a fantastic infographics looking at the resources that we have across the board of a number of different materials. So I don't know, maybe it's a bit small, but you have here rainforest, coral reef, agricultural land, coal, oil, gas, and then different materials such as aluminum, phosphorus, tantalum, titanium, copper, salt, silver, indium, and antimony. And what you see here is the lifetime, the life that we can continue to exploit these different materials. And you can see here that if we think about the rainforest, for instance, we actually okay, I'm going to start with antimony, which we don't have a lot of years left of. It's only 8 years. Indium is 12 years and 70 years for silver because we have a really heavy use of these various materials, right? This is the estimated number of years that we have left of these particular materials. The oil and gas we estimate to be gone in about 40 years. And the rainforest can last for longer. But again, we see that even the agricultural land is actually estimated to be, maybe we're going to run out of it in 67 years. So that's really some pretty dire projection because we're going to be in big trouble. So what this tells you is that we really need to go beyond this linear thinking and really need to do the circular economy because otherwise we're really going to run out of these resources. This is another area of another way to look at the same problem where you look at different elements here in the periodic table and you can look into them versus the vulnerability to supply restriction. So that means how vulnerable they are to not having enough resources versus the supply risk in the long term. So this is the numbers that we had earlier in terms of number of years. And finally, environmental implications of the use. So you will find that, for instance, gold here has a high vulnerability to supply restrictions. Also, it's going to run out fairly shortly in a range of maybe 40 years. And the environmental implications are pretty dire as well. So you can find here some other way of looking into the same problem by highlighting the different elements here, their performance, and how they've been applied. And another angle to this too is that because of these poor design principles that we have and the way we use chemicals, we have been ready to accept, all of us, that pretty toxic chemicals are used because of the function that we want to achieve. So in the umbilical cord of newborns, they have detected 287 different chemicals, 180 of which are known to cause cancer in humans and animals, 217 of which are known to be toxic to the brain and the nervous system, and 208 have been being associated with birth defects and abnormal development in animal tests. So this is to tell you that we are surrounded by these toxic chemicals right now. They're pervasive, and they even are inside the umbilical cord of babies. So, and this makes me think about this new development right now that we have of perovskite materials. These are materials that we want to use to replace the silicon-based solar cells because they're allowed to make, for instance, flexible systems, which is really exciting. But the issue with that is that it contains lead. And you're talking to people in that field and they're like, yeah, but it's fantastic. Perovskite is going to save us from this and that. And we're going to be able to manufacture it better. It's going to cost less. It's like, yeah, but guys, you're going to make a material that has stoichiometrics in it or lead. That is associated with Saturnism, which is a horrible disease. And we got rid of these types of diseases by getting rid of lead paint. And it took many decades, even in the United States, to get rid of that. And now you want to bring it back by the back door through the solar industry. I mean, this is causing massive philosophical challenges. I mean, are we going to do that? I don't know. So this is really something to think about. Another consequence of this linear processing is also the way that we're making molecules without looking at consequences. One of them is the generation of waste. And in particular, in the pharma industry, pharma, again, is really driven to function. You really want the drug to occupy and to make the material that you want by being active for, again, curing cancer or lowering your cholesterol or whatever. But in order to make 1 kilogram of medicine in 1990s, you have been using 1,300 liters of solvents. All of these solvents here, you can see they're terrible. So this is really, again, a testimony of the way people have been doing this. The situation, by the way, has largely improved. This is a number from 30 years ago. There's been lots and lots of efforts by the pharma industry to reduce these numbers and also reduce the use of solvents such as DCM here. So there are some nice stories to tell about how this is better. But again, initially, the way they've been designed as being really linear, as being really focused on the function and not so much on everything else, has led to these types of unwanted consequences. Sorry about this. So again, we discussed this notion of waste in the context specifically of solvents, but of course, waste can be expanded to all sorts of waste that we have around. For instance, plastic waste, which are huge, and we really struggle to handle either via recycling. It is still mostly landfilled when it's not actually ending up in the environment and causing really horrible consequences, such as here, this consequence to the turtles. But we know as well that in the environment, they transform into microplastics, nanoplastics. There was a report just last month explaining how we have in all our brains the equivalent of a little Lego piece, a little Lego man that is the amount of plastic that we all have in our brains right now in the form of microplastic. It's pretty stunning. And this is coming from the fact that some of these plastics end up in the environment in the form of microplastics and again invade our brains. Of course, waste in the form of pollution as well is really pervasive and happen to all of us. Another part of this is also this notion that if we don't see it, it don't really exist. So a lot of problems that have happened over the years around chemicals is that we've not been able to see some of the consequences of what was happening. So this is an example taken from the history of the United States with chemicals, where this canal, the Lost Canal, has been heavily polluted with different chemicals, causing locally a lot of backlash and eventually leading to changes about pollution prevention in this place. Different disasters have been really critical as well in thinking about this. What's called the biggest chemical accident in human history happened in India in a place called Bhopal. There were 16,000 casualties and 500,000 people were injured by this runaway reaction, which happened in this locality. And it really was a horrendous disaster. The issues that happened there were the design, the fact that the storage of an intermediate for this reaction was not done properly. There were issues with the integrity of the buildings, the mechanical integrity. There were issues with staffing. There were not enough people to actually check on things and raise awareness and raise the alarm when something didn't work properly. And the response capacity was largely inappropriate when the disaster happened. So this is the reaction that happened with methyl isocyanate, which was the intermediate that was used in the reaction in Bhopal, and the runaway reaction that happened with water caused this terrible disaster. Another disaster that happened more recently happened in Beirut 4 years ago, where there was a fatal explosion in the port of Beirut. So this is the city of Beirut here. This is the port. In these large containers, they stocked 2,750 tons of ammonium nitrate, which is used as a fertilizer. In fact, there were lots of issues with this particular material that had been confiscated 6 years prior to the explosion and never moved for all sorts of reasons. And that meant that it wasn't really properly taken care of. When the explosion happened, 218 people died, 7,000 were injured, and 30,000 people were displaced. And you can see why. I mean, look at this image here. You have an explosion here and you have a massacre there where the explosion was felt for kilometers around. So all windows were shattered. People felt it was falling on them. It was really bad. And it's considered that there was $15 billion in property that were damaged during this explosion. And this is a photo of the actual explosion here. This is the reaction that happened. So the ammonium nitrate, when it is heated, can actually undergo this decomposition pathway, which actually generates an explosion as it happened. Another really interesting example is what is happening in Ghana. So all the waste that is generated from electronics around the globe are typically shipped to different countries. And there are several countries who will collect it, but one of the best known is actually Ghana, because it is an open society, and any journalist can go to Ghana and have a look at them. So in Ghana, and especially in Agbogbloshie, you have people who are collecting the waste, and what they do is they burn the computers, like used computers, in order to get rid of all the organics and collect the metal that is in that. And of course, in doing so, there's lots of very toxic fumes that they have to be exposed to. And of course, this it exposes them to lots and lots of toxins, chemicals, persistent organic pollutants, but also lead. This is an example of how the entire supply chain is actually it's designed in a way to generate highly polluting situations for people. So chemicals accidents or disasters result from bad management, they result from poor design, they're inherent to the fact that hazard is not handled properly. And this is why it leads to fatality. So what we're going to talk about a little bit is this notion of risk now, and try to formalize this a little bit in a little bit more. So The risk to environments can be defined as the exposure of the environment to various pollutants. We discussed CO2 and climate change earlier. This is another one of them, where plastics are released into the ocean, creating these, we often call this the seventh continent, because this is where plastics are accumulating in the big oceans, in the middle of the ocean. There's also risk to human health via exposure to chemicals, direct exposure, or also risk to the stable environment via the release of greenhouse gases, such as CO2 or methane, which are going to trap heat close to the surface of the earth and cause a change in the climate as a consequence. So when you think about risk, there's a way to do it in a formal way, and that is by considering that risk is a function of hazard and exposure, right? So hazard is how dangerous a certain compound is, and exposure is how much you are going to come in contact to this molecule, right? So exposure is something that we typically handle by saying, okay, we're going to make sure that you're not going to be in contact by putting some distance between you and the chemical at question. So typically what people do is they're using, for instance, scrubbers for sulfur. So in this case, you have a chemical situation that is happening, and we're going to put a filter or something that is going to make sure the toxic compound is not going to come out. Or we're going to have what's called personal protective equipment, making sure that you're protected from touching the chemicals by some gloves, by some plastic, big clothing. But of course, you understand here that it's not that we remove the hazard from in and of itself. The hazard is still there. It's just that we're going to control the exposure alone. So, but if this exposure control fails, let's say if your PPE is torn apart, or you forgot to put it, or I don't know, someone enters the lab without putting the proper equipment for whatever reason, or if the scrubber doesn't stop what's working and no one sees it, suddenly your risk is going right up, skyrocketing instantly, because the hazard is still there. So this is the problem that green chemistry is addressing directly. When you consider only the exposure and not the hazard, you are creating these conditions for all the accidents that we thought about earlier, all the accidents we had before. There were measures of exposure limitations, but they failed. And when they failed, the hazard was there and the risk was at the maximum. So we need to focus on reducing risk by reducing inherent hazard. That's the way that's the way of green chemistry. Oh, sorry. So some of the ways to reduce this hazard is actually look at it. So you remember the LCA, life cycle assessment we mentioned? In life cycle assessment, you're going to assess the hazard of chemicals based on what we know of their toxicity, right? So toxicity can happen in so many different ways. So you have, so this is even more general than that. It's the full hazard categorization. So the reason why I refer to LCA is because this is the hazard characterization that we also use in this. So within this, you have human toxicity hazard. So you recognize things that you know: carcinogenicity, neurotoxicity, hepatotoxicity. This is your liver. Nephrotoxicity. Thank you so much. I had the name in French in my head. Cardiotoxicity to your heart, hematotoxicity to your blood, endocrine toxicity. This is to your enzyme, and so on and so forth. Then you have environmental toxicity. So this is considering the toxicity to the environment. So to algae, to fish, to etc. So aquatic toxicity, this is to aquatic life. Avian toxicity, this is birds. Amphibian toxicity, it's amphibian, and so on and so forth. Phytotoxicity, it's plants. Then you have physical hazard. So can it explode? Can it corrode? Can it oxidize, reduces, and so on and so forth? And then you have global hazard. So you recognize here some of the things we discussed earlier: acid rain, global warming, ozone depletion, some of the things you find in actually the planetary boundaries. So the toxicological hazards can be qualified actually as coming from 3 different origins. So when something is a toxic agent, it actually may come from a chemical toxicity, such as cyanides. It can come from physical toxicity, for instance, radiation, or it can come from biological toxicity, such as, for instance, snake venom acting as a biologically active material against you. All of this toxicity can also be enhanced or reduced as a function of how persistent the agent is in the environment. So if you have a material that persists in the environment, then it won't be easily, it means it's not being easily degraded. And that's often because this is a non-natural product. So there's no mechanism by which nature knows how to break it down. And what will happen is that it will cause more problem, especially if it is inherently toxic. For instance, DDT. So DDT is a toxic material that also is persistent. So we do find in the environment today DDT that was released 40 years ago, 60 years ago. So even now that we have regulations to not use DDT, we'll still find it in the environment. A material may be inherently non-toxic, but still persistent. Polyethylene is a good example of it. And even though it's not toxic in and of itself, it could lead to toxic properties, such as the transition from plastics to nanoplastics, which we now know is associated, for instance, when it goes inside the body, to some inflammation. So toxicity and persistence can be related and amplifying, actually, the existing toxicity. And that will happen via, for instance, something called bioaccumulation. So here what you see is that as a persistent, for instance, pollutant goes into the environment and is uptaken by, let's say, a little fish here or krill, some bigger fish can eat it, and then the bigger fish will eat it, and eventually the human will eat the bigger fish. So this is really causing what's called bioaccumulation, which is the fact that a living organism will actually accumulate more and more of it, especially as it is persistent. So another aspect is, so as we are looking into reducing this hazard here, it's really important to remind ourselves that green chemistry is really about trying to address this question of design. So in green chemistry, the definition of green chemistry is the design of chemical products and processes that reduce or eliminate the use and generation of hazardous substances. So by definition and by design, green chemistry actually addresses this question of reducing the risk by reducing the hazard as opposed to reducing the exposure. So design here is intentional. So the conventional approach to dealing with hazards and hazardous substances, so reducing the risk by minimizing exposure, for instance, for equipment, but here we want to reduce it by reducing the hazard. So if there's no hazard, exposure becomes irrelevant. So why does the chemical have to be volatile or toxic? Well, it doesn't really have to. If you design it to not be that way, then you're going to address your risk right away. No hazard, no exposure, no risk. If you can master the design and the synthesis, why don't we aim towards eliminating all the hazards? Well, I think that's a nice objective, right? So some of this idea has been developed here through this paper around designing tomorrow's chemical for designing out this hazard. So this is a way with which you can actually think about this by saying, okay, so I want to make a material. And the first thing that you need to do is you need to think about the function, right? So I want to make a material so that it's an antibacterial thing that I'm putting in my toothpaste, I don't know, or I want to make a drug that's going to have some biological activity. So, okay, you go and you provide the desired function. So, does it provide the desired function? No. Well, you redesign your material until you have the function you want. And once your molecule has the function you want, you'll go to the next step. Is it made from depleting resources? If it's made from depleting resources, then maybe you need to redesign your system by including renewable feedstock. But if it's made of non-depleting resources, you can go to the next one. It's like, oh, is it toxic? If it's toxic, yes, you go back to the drawing board and design it. If it's not, then you can continue. Is it high complexity? Is it high embedded energy? And then if for all of these you say no, you can say I have an I have sorry. And the last question is it environmentally degradable? And if the answer is no, go back and again redesign the system. So that's one of the ways with which you can really start to take out the hazard from the design by the design principles, so that you would have function, renewability, non-toxicity, biodegradability, and function again. Function matters. Function is important. So hazard must simply be recognized as a flaw in the design process rather than something we accept because we want to make the function, right? Green chemistry moves our consideration on how to deal with environmental problems from circumstantial to intrinsic. Circumstantial is a way to see life as depending on the situation. This is where you say, okay, I'm going to use this chemical, but it's only going to be used in a lab where people are going to wear PPE, where people are going to respect the rules, where people are going to come from 9 to 5, where people... And this is, circumstances don't always happen this way. We know that one day this chemical can be in contact with a baby that doesn't have all of these criteria, and suddenly there's a big problem. So you want to move from these circumstantial, which is based on use, exposure, handling, treatment, protection, etc., to actually intrinsic. There's no toxicity because you design it out. There's reduced ability to manifest hazard because you designed it out. The inherent safety is there's no accident or terrorism because you've made it to be safe to begin with. And finally, you can make profitability because all of the risk is out, and you don't need to have so much money spent into these PPEs and these protective measures and trainings and so on and so forth. So there's even economic benefit to doing that. So what we need to do is we need to fulfill the function while we are removing the risk. And if we leave the status quo, we're not going to be able to do that. But if we invent a new green chemistry, then we're able to combine two sides of this world. So this is what we have to do together. And this is why I believe we can make that transition together. And I am asking you to try to work towards this goal today. Right? Are you motivated? Good. So what have we seen so far? Planetary boundaries. Now, who doesn't know planetary boundaries? Right? No one. Good. I like that. Socioeconomic trends, UN SDGs. You know that. Greenwashing, you remember? Right? Introduction to circular economy and recycling. Introduction to life cycle assessment. And now today we saw everything is chemical, the purpose of chemistry, function versus consequences, the status quo, accidents, risk, and finally time for a change. Yeah. So now let's discuss. Can you remember how greenwashing, has affected you personally? Do you have a story to tell about that? Anyone? My friend Liga?
Yeah, because we are usually make it easier to claim that it's a green without any life cycle assessment. So to avoid this greenwashing, it goes like LCA and are the quantitative insurance.
Thank you so much. Fantastic. Yeah. Woo! Anyone else wants to talk about a greenwashing experience they've had? Yeah, go ahead.
I have one, and I think it shows how perhaps sometimes the public doesn't understand what is the better or worse thing to do. So when I first started studying the environment, my mother, who supports me a lot, make sure you thank your mothers for everything they do. She said, Matt, I'm now thinking of the environment. So every night, what I do is I unplug my phone charger from the wall, and then in the morning again, I plug it back in. I was like, thank you so much for supporting me. And then I sat down and I did the math of how much energy that actually saves. And what I realized was that 1 second of driving a car is more energy than she saved by doing that every day. And I think we've been told a lot that these small actions do a lot of things, but it's not one to one, right? Like unplugging your phone charger for 8 hours does not cancel out driving in a car for 1 second or 10 minutes or an hour. And I think that's something that perhaps is kind of brainwashed over everyone's perspectives, the equality of the substitution between individual activities.
Yeah, thank you so much for this example, Mitch. Yeah, great. Yeah, you can clap from that. Anyone else is a good example of greenwashing? You have one? Yeah, the mic is here.
Okay. Uh, uh, Sometimes I know it was greenwashing, but just to make myself feel better, I just follow. I think that's the experience
Yeah.
about greenwashing.
Yeah, no, and that's really interesting, because we do this to we know it doesn't really change anything, but we do it because we feel good about it. And I think we we have sometimes to question what our brains are telling us to do, right? Sometimes our brain are like, how our brain functions, and it's been designed to sometimes have a very fast response so that it will save our life. Literally, when we are in a life and death situation, we will make a fast decision. But sometimes these decisions, we need to think about them. We need to calculate. And our brains are not our best allies sometimes. They want to take shortcuts, right? And this is a bit what you're describing here. So question things, guys. Look around, ask questions, be inquisitive, because this is how you're going to grow and make better decisions. Okay, thanks a lot for this discussion. Big round of applause for my friend here. So what do we see as the main roadblock for reaching sustainability? What's the roadblock? Why can't we do all of these beautiful things we've been discussing? Yeah, students.
Maybe from dari kehidupan sehari-hari, kira-kira gimana sih? Kan kita tahu ya sustainability gitu. Kira-kira apa sih dari kehidupan sehari-hari aja? Nah, yang teman-teman rasakan sebenarnya gue bisa nih berkontribusi lebih gitu. Tapi kok enggak gitu. Gimana kira-kira hal-hal small things, like right. I always give it a ya ya silakan. Ada? Anyone? Boleh.
Uh, my name is Adina Rika and I'm from Chemical Engineering. I think uh, the most we do in uh, everyday life is using recyclable products.
Recyclable products, okay? What's the main roadblock? Apa ya yang menjadi hambatan kenapa kita nggak pakai recycle gitu?
Resources is not as
The resource? Okay. Okay. So maybe using recycles. Okay. Any other? Mungkin dari kehidupan sehari-hari mungkin. Misalnya dari naik kendaraan. Ada? Boleh? Aditya juga boleh loh. Boleh, boleh. Kita sekalian. Tuh, kena deh. Iya. Ya. Boleh pakai bahasa Indonesia nggak, Pak? Saya bantu terjemahkan, jangan takut. Boleh. Nah, boleh sebutkan nama dari mana?
My name is Hasbi. I think what we can contribute to be more green, or maybe to reduce our carbon footprint, is to use public transport in everyday life.
Transportation. Terus yang menjadi tantangan menggunakan public transport apa contohnya? Hasbi sendiri
Uh,
gimana hari-hari?
I think most of the time I wait too long for bus to arrive. But
Time.
the time, and also maybe we have to educate the people in our country to be more inclusive about the jalur busing.
Yes. Okay, thank you. Yeah, as I said on the car on the way here, we would like to rely on public transport, but sometimes the system itself is not reliable because the time is unclear. Like what is the time the bus will arrive or the angkot. So it's easier to take your personal transportation, like those kind of things. So it's systematic, but also sometimes ada juga kenyamanan ya nggak sih kadang. Sometimes people tend to use, okay, I'll just use my own transportation because it's cleaner, it's more efficient. But at the end, there's traffic and everything. But despite of that, people still choose to use.
Yeah. So
Yeah,
that's definitely a
transportation.
main roadblock
Yeah.
to reaching sustainability is that some of the systems that are greener are not always well designed. And I mean, public transportation is one of these examples where if it's not done at the really large scale, it's not efficient. To be a good alternative for people. Absolutely. And did you ever feel exposed to the risk of a chemical accidents? And what were the underlying hazards? Do you have stories to tell about exposures, hazard?
Ada mungkin dari perusahaan atau teman-teman mungkin di industri atau teman-teman ayah, boleh silakan.
Boleh pakai bahasa Indonesia dan saya bantu ini sharing aja ya. Mungkin kalau di pabrik cat itu kan memang berhubungan langsung dengan bahan kimia seperti itu. Memang untuk mendorong orang untuk aware terhadap bahan kimia itu memang sedikit sulit gitu. Jadi perlu dibiasakan seperti itu. Memang awalnya suruh pakai PPI, APD gitu, agak susah seperti itu. Nah, baru kita di stepnya itu diberikan pengarahan, diberikan anjuran pemakaian APD karena akan menyebabkan pada penyakit akibat kerja seperti itu, diberikan arahan seperti itu.
Terima kasih dengan Ibu yang. Okay, so she said about the paint industry, because we understand that the paint industry is full of chemicals, but sometimes the workers, they need to be re-educated about using safety gloves, devices to protect yourself from contaminants like that. So they have to keep socializing and educating the workers that it's not safe, it will impact your health. So things like that. Yeah, very good. Okay, any other? Maybe? Yes.
Maybe about the thermometer, but using the mercury. Yeah, it's happened to break. Then after that, we change all the thermometer using non-molecular material.
That's a great example. Yeah. I had the same in the lab where I did my PhD, where we broke it, and then we eventually changed all of that to have non-mercury based thermometers. Absolutely. So that's a great example of removing the hazard altogether. Right?
Any other? Any other? Oh, for myself.
Yeah, go for it.
For the greenwashing. Like,
Yeah.
sometimes the paper cups, they actually have plastic, what you call it? Yeah,
Rim
I don't like that. And then several times ago, in Indonesia, we started using paper straws, and that actually contained contaminants also, right? And then we stopped using that, and then switching it to stainless straws, right? And then also, there's another impact. Sometimes we use tumblers, but sometimes people keep buying tumblers, and we know that tumblers have more effect, right? So like about that, so that sustainability in using one product, for a long time. Yeah, absolutely.
Well, great. Thank you so much. So I think this helps close this session. So thank you so much for your your participation in the discussion and your kind interest. Oh, you have another question. Yeah, go ahead, Ruth.
I have a question. I was really wondering when you talk about the design, uh, when we are doing design, we always have this kind of trade-off between the functionality, of course, the trace of the materials. So, is there any lines of suggestion or guidelines for to what extent can we approve the functionality over this traces of materials and process and so on? Because it's to me, it seems to be like when we are doing some quantitative analysis, CSE, and we are only comparing which one is better over the good ones, or which one is worse over the bad ones. So, and at that point, we cannot really judge or determine, like the example of perovskite that we mentioned, and when is it really okay if we use lead-based materials? For some people, it might be okay. For some others, it might not be okay. But is there any like global standards, or this common understanding, or on how we proceed on these design trade-offs? Thanks.
So thanks a lot, Rufi, for your question. My understanding is that there's no absolute answer to that question, and it's really case by case basis. And this is why people say these LCAs are never going to replace a human being making a decision on the system. This is really important to understand that, because there's no free lunch. You're gonna have to make a decision if you want to have the lead or not. And if the benefits you have from the performance standpoint benefit, then you take. And things change. So there are other tools like alternatives assessment, for instance, where in alternatives assessment we consider function as one of the criteria. So you can in one thought compare functionality versus these other risks. But at the end of the day, you, Rofi, you're going to have to make the decision. No one is going to can take the responsibility out of your hands.
Thank you, Farofi, for the question. Yeah. So at the end of the day, it depends on us on making the standards. Yeah. How much we can use those chemicals and what will be the effect, because I think that everything that we do, we will have an effect to the environment. It's up to us to make a better decision, and which one has a lower impact to the environment. I think that's it. Yeah. Okay. So again, terima kasih. Thank you, Audrey, for your session. Terima kasih again for the prayer. Okay, so mungkin sedikit tadi saya mau I asked permission to give a summarize in Indonesia a little bit. So again, dari sesi ketiga tadi kita sudah sepakat bahwa semua ya yang ada di dunia ini itu dari bahan kimia gitu ya. Dan tentu dari setiap keputusan yang kita ambil, yang kita lakukan, tentu itu ada dampaknya, baik positif maupun negatifnya. Nah, tadi yang harus ditekankan adalah tadi linearitas gitu ya, bahwa kita tidak bisa hanya mengandalkan nanti fungsinya ketika produk itu jadi, tapi kita juga harus memperhatikan dampak sebelum dan setelah kita menggunakan produk itu. Nah, itu masuknya sirkular di situ, kita harus memikirkan dalam proses mengurangi efek lingkungan, ya, efek limbahnya seperti apa, dan juga setelahnya. Lalu tadi ya diberikan contoh, apakah kita menciptakan produk ataukah kita malah menambahkan limbah gitu ya dari efek atau produk yang kita hasilkan. Dan tentunya ini semua kita harus masukkan ya bahwa kita tuh harus mengubah pandangan bahwa tidak change of perspective tadi ya sebagai itu adalah sebagai suatu kekurangan dalam merancang proses. Jadi yang di-highlight di sini adalah bukan hanya produk akhirnya, tapi kita juga melihat dari prosesnya itu apa yang harus diperbarui, apa yang harus diperbaiki karena berarti tadi ya kita efeknya adalah kita ingin mengurangi efek terhadap lingkungan, kita ingin mengurangi limbahnya, tapi tetap mencapai functionality dari produk yang kita hasilkan. Seperti itu. Jadi dan kita embedded tadi apakah berdasarkan situasi ataukah sebelumnya kan kita melihat situasinya, tapi harusnya change of mindset-nya adalah kita lihat, kita harus integrasikan itu di dalam desain, gitu ya. Mungkin itu summary-nya, a little summary for me in Indonesian, so maybe the students can also understand of the material. Thank you again, Audrey, for the session. And